Hi everyone, this is Azure Biosystems. My name is Jan, and I will talk today about fluorescent Western blotting. Azure Biosystems is a California-based company, and we focus on giving you raw data you can trust with a better fluorescent Western blotting workflows. And I will talk today about fluorescent Western blotting. But first, let's have a look what makes a fluorescent Western blotting different from a standard ECL detection. And what are the different flavors of fluorescent Western blotting, like the direct detection and protein stains? And then we'll have a look at a fluorescent Western blotting itself, certain tips how to do your protocol better, and briefly about imaging systems. And there'll be a link to additional resources in the end. So Western blotting has been here for a long time. It's a great technique if we want to detect a protein of our interest. The usual chemistries are ECL, the enhanced chemiluminescence, and fluorescence. We call it RGB or infrared, depending which colors do we choose. The ECL stands for enhanced chemiluminescence. And as the term implies, it may be actually it's a light. It's a chemical enzymatic reaction to produce a luminescence, which is a light. Usual enzyme used in this reaction is an HRP, a horseradish peroxidase. And because it's enzymatic reaction, its detection limits for this are very, very low, as low as low femtograms. But because it's enzymatic reaction, the reaction is quite dynamic and unstable in time, which makes it sometimes less reliable to quantify. And the biggest drawback is we can only detect one target at a time, which is a great drawback. ECL is enzymatic reaction, which have to be careful not to load an excess of protein, because then from the high abundant bounds, we can actually get a quick decrease of a signal, which may lead to a wrong quantitation on the blot. And because it's enzymatic reaction, we have to be careful about concentration of the substrate, the temperature of the reaction, and the optimal pH in the solution. And last but not least, the most important is the choice of a substrate that purely defines what kind of data we get from our ECL Western blot. If we choose a stronger substrate, which will see a different range of information than if we choose a less sensitive substrate. It also, we have to be careful about how linear a substrate is and at which range it depletes and which range it cannot actually visualize. Each substrate is different. And also we have to be careful that certain substrates decrease in stability very quickly. So we should test this to be aware if our substrate is not depleting too fast. So there are three things that we have to keep in mind when choosing the right substrate. First is the substrate strength. How strong is the substrate? If it detects a low abundant or high abundant proteins, and which range of the proteins it will visualize well. Then we have to look at a substrate with a slower decay if we mean to detect for a longer time. And we have to check for the signal linearity of a substrate, especially if we want to compare or semi-quantify the results on the ECL blot. I'd like to mention that there is not one substrate that can cover all your needs. So for example, even at our Azure Biosystems, we have designed 3 types of substrate. The Radiance ECL, which is the economical substrate with signal longevity and linear signal. The Radiance Q, which is the perfect milligram for sensitivity and a wide dynamic range on the other hand. And Radiance Plus, if you needed a very, very low amount of protein to be detected. This one is perfect for very low abundance proteins. As I mentioned before, the biggest drawback of a chemosense reaction is that it cannot be used for detecting multiple targets at a time. I'm fully aware that there are certain workarounds. One of them is cutting the membrane in two, and another one is stripping reprobing. But we have to keep in mind that either of these methods produces irreproducible results sometimes, because we are not detecting the same blot anymore. We should avoid stripping or reprobing when possible, and only if we have to. We should choose commercial stripping buffers to get a better performance than a house-made solutions. So if we cannot use stripping or reprobing for detecting multiple targets at the same time, what should we do? And there is the main reason why we are using a fluorescence detection, which is the focus of today's presentation. So how it works, instead of an enzyme, we have a fluorophore linked to our antibody. And because it's a fluorophore, it reacts to a certain excitation wavelength. It could be a laser or a different light source. And then it gives us a signal, which is a linear function of a concentration of the target, which is perfect for quantitation. The drawback is that it may be less sensitive than chemomedicines in certain applications. However, that very much depends on your protocols and your whole assay. Still, the detection limits usually achievable are usually in tens of femtograms, sometimes even in single femtograms. And it's very reliable for quantitation. And you can detect multiple proteins at the same time, which is the greatest benefit of the fluorescence detection. Stability and time also allow us to even archive a signal. So if we prepare our blot well, there should not be any much change in fluorescence signal intensity within hours from making the Western blot, which is perfect because not always in our lab we can perfectly time when we can detect our Western blots, and this gives us further flexibility. And in fluorescence, we can detect this multiple target at the same time, which we call multiplexing. We can multiplex the two proteins in time, like this alpha-stat and phosphostat. Instead of doing stripping or reprobing, we can probe them with a fluorescent antibody and detect them at the same time, even if they are overlapping in their sizes. Choosing the right fluorescent dyes and the right detection means can help us differentiate these signals very well. Or we can combine these two targets with an additional normalization control, like a reference protein, seen here in blue, or experimental stain, like a total protein stain, which we see in the image on the complete left. And there are multiple choices of fluorescent detection channels, as we call them. And a visible, which we sometimes call an RGB, red, which stands for red, green, and blue. We can detect a blue channel. This is a blue excitation, green emission, like a cyanine 2. The green channel, as we call it, which is a green excitation, red emission, for dyes like cyanine 3. And the red channel, which is the red and far red emission, like Psi5. And then there are two infrared channels, 700 and 800. There are multiple secondary antibodies available in the market. I'll give this as an example from Azure Biosystems that we have for 3 dyes in a red, green, and blue, and 2 dyes in infrared. And there is usually a lot of different species to choose from. There's one thing to keep in mind. If you prefer to detect your phosphorylated proteins with fluorescence, it's very important to choose a detection means that doesn't have a crosstalk itself, and for sensitivity, it has the best signal-to-noise ratio. And for this, we can highly recommend detecting a fluorescence infrared with a laser-based detection because it has a minimum crosstalk, giving a perfect way to detect the phosphorylated proteins. So generally, just let's have a look back. So we can detect a fluorescence detection with RGB or infrared dyes, or both. The usual advantage of the RGB is there's much more choice of antibodies and wider protocol flexibility, and there's a lot of different imaging systems and scanners can detect these. The challenge is that usually there is a higher autofluorescence in this channel. While in the infrared, we have a lower autofluorescence generally, which gives us a better sensitivity and better limits of detection. But we need usually a stronger excitation, that not every system can give us a good infrared detection. Usually the laser is the great way to detect the infrared. So we have discussed the differences between indirect detection with ECL and fluorescence. And now the question is, what is direct Western blot? Well, direct Western blot is when we are using a labeled primary antibody, which is different from using a labeled secondary antibody, which is the normal protocol we normally choose. When do we use it? Well, if we have a great antibodies, but we cannot use them because they were raised in the same species, and then using a standard fluorescent Western blotting protocol with secondary label, with labeled secondary antibodies doesn't really help us. So in this case comes the direct Western blotting that we can label both primary antibodies and very easily differentiate them. And what it also gives us, because we are using primary antibodies, if we need it, we can use still the sensitivity of a secondary ECL detection. So we can still probe with the indirect ECL detection and follow that after detecting with fluorescence with the primary antibodies. So how to label your antibody? Well, there are labeling kits available. So you can take the labeling kit and label your own antibody, and then use it for your protocol. How simple. So what are the advantages of direct versus indirect Western blotting? Well, I would say generally, if you do not have to, and you don't have any problems with cross-species reactivities, the indirect Western is the first choice. It's just more common protocol. But you have to be careful that there is always a potential for cross-reactivity. If it is, then the direct Western is a viable alternative that can help you to overcome this cross-species reactivity. But in order to use that, you need to label your primary antibodies. So indirect Western is the common choice, but direct Western can help you in case the indirect Western cannot be done on your sample of interest. I also like to mention something about total protein stains. Total protein stains are a way to help us to normalize or check for the uneven loading of the proteins on our Western blot. And for example, here is a list of a lot of different total protein stains. The stain that stands out is called Azure. It's based on epicoccanon chemistry, which gives it a great range of sensitivities from 0.1 micrograms up to like tens of micrograms, which is a great dynamic range. And Azure is quite quick and it doesn't shine when it's not bound to proteins. And it also can be easily disposed, and it degrades very easily biologically. The Azure has a dynamic range up to 4 orders of magnitude, which gives us a great possibility to normalize our Western blots to something else than a standard housekeeping proteins. But there is more about normalization, and my colleagues will be talking about that later. So let's focus on the fluorescent Western blotting itself. There are certain protocol tips that can help you to make your fluorescent Western blot a success from the first try. Dilute ladder is a great thing to do if you're moving your protocol from chemiluminescence to fluorescence, because a lot of ladders actually shine in the fluorescent channels. It's good to dilute it at least 10 up to 50 times before loading on a gel. Or consider leather that doesn't shine at all, or at least shines in one color. And loading dies can shine a lot too, so please be aware of that. Cut it off the gel before you put them on the transfer. And low fluorescence PVD membranes can be highly recommended for using in these applications. And always handle your membranes with clean plastic forceps, because the fluorescent Western blots sometimes can bear show artifacts. And transfer system, we can highly recommend using a wet transfer system, though we see that a lot of users use semi-dry systems as well. Just be careful that semi-dry systems sometimes produce a lot of heat, which generally creates a high and non-uniform background. So double checking this with your transfer conditions. If you need to do a fast transfer, you can opt for a wet transfer with a faster transfer buffer. For example, the Azure transfer buffer can give you a transfer times down to 20 minutes in a wet tank, which is actually amazing. Blocking is also a very important step for fluorescent Western blots, because the fluorescent antibodies actually adhere easier to the membranes. A blocking step is crucial to avoid that residual signal. So using a commercial blocker can help you significantly reduce the amount of background you can get in your fluorescent Western blots. And we can highly recommend using something like incubation trays. They can protect your precious fluorescent Western blots away from light, so they do not quench that easily. Where there's a lot of resources about primary antibodies, I would just mention that you should use a well-characterized antibody. Don't use too high concentration of primary antibody. And if needed, use a 4 degrees temperature and incubate overnight to reduce a non-specific binding. With using the secondary antibodies, avoid any cross-reactivity. Avoid antibodies that are too close, like anti-rat and anti-mouse, or avoid secondaries for the animal in which another one was created. So do not ever mix goat and anti-goat antibodies, because that would give you an unspecific bindings. And wash. A stringent wash is the most important part of your fluorescent Western blotting workflow, because of fluorescent dyes can adhere to a membrane. The volume and duration of washes is really important. Instead of doing 1 times 5, 15 minutes, do 3 times 5 minutes and always remove the washing buffer. And final rinse is the most important, because a lot of detergents, like Twin 20, can both fluoresce in detection, but some of these can also decay your fluorescent signal over time. So rinsing in a clean PBS or TBS after your washing for the final wash is very highly recommended. And after this, because the fluorescent detection works best when the membrane is dry, you can dry your membrane. Usually drying with methanol or ethanol can do this faster and removes more water than the air drying alone. And when using a methanol, please proceed and with caution, because this is a dangerous item. Once you dry a membrane, the stability of fluorescence stays unchanged for hours. But it's important that you remove all the detergent in the previous step in washing PBS or TBS, and this can help you to keep the stability of fluorescent signal for over months. And if needed, you can use something like a quenching sheet that we provide to reduce the fluorescent background. There's a lot of kits available from Azure Biosystems with blue, green, red colors on 700, 800, mostly for anti-mouse and anti-rabbit. Feel free to get in touch with us if you wanted to try. And of course, the last step is using the detection system. It's very important to have a system that can very sensitively detect the antibodies that you have. Whether you have a camera system, like we have the Azure Imager, we can very highly recommend to use If using a camera system for phosphorated detection, use the infrared part of Spectra and preferably use a system that has a laser-based detection, like the Azure 600 we see here. Or use a laser-based scanning system like Sapphire from Azure Biosystems. There are 4 laser channels and all 4 detected simultaneously. Azure Biosystems also makes these imaging systems, the scanners and the imagers, and would be happy to provide them for Blots and way beyond. And for additional resources, please go back to azurebiosystems.com, where we have our Western Blotting Guidebook you can download, quantitative Western Blotting basics, and checklist for your quantitative Western blots. And feel free to get to us if you have any questions. We wish you great success with a fluorescent Western blot.